Look up at the stars tonight, and what you're seeing isn't just light, it's a message from the distant past. Every flicker, every gleam is a story that began its journey to your eyes millions, even billions of years ago. These aren't just points of light, they're ancient travelers carrying tales of cosmic explosions, distant worlds, and the birth and death of stars. Think about that for a moment. When you gaze at the night sky, you're literally peering into a time machine where the light itself is a relic of events so old they predate the very ground beneath your feet. What if I told you that some of these stories, written in Starlight, have only just reached us? That right now, as you watch, the universe is whispering secrets from an era before Earth even existed. Among these celestial narratives are 22 extraordinary chronicles, each one a breathtaking snapshot of the cosmos at its most dramatic. Supernova that outshone entire galaxies, quasars blazing with the energy of 1 trillion suns, even the faint glow of planets orbiting stars so far away, their light has been traveling since before the first dinosaurs walked our planet. These aren't just facts, they're fragments of a grand, unfolding epic, and tonight we're going to piece them together. This journey isn't just about astronomy, it's about connection. Every one of those distant points of light ties us to something vast, something timeless. The atoms in your body were forged in the hearts of stars, which means you're not just observing these stories, you're part of them. So let's step into the cosmos together, unraveling the mysteries carried across the ages. By the time we're done, you'll never look at the night sky the same way again. The universe has been waiting billions of years to share these tales with you. Are you ready to listen? The first story in our celestial anthology begins with a blaze so bright it would have outshone entire galaxies if there had been any to witness it. Billions of years ago, in a corner of the universe still dark and raw, a massive star reached the end of its life in the most spectacular way imaginable, a supernova. This wasn't just any stellar explosion. It was a cosmic alchemist's furnace, forging elements like gold, platinum, and uranium in its fiery heart before scattering them across the void. Today, the faint whisper of that explosion's light finally reaches Earth, carrying with it the signature of those heavy elements, the very same ones that now course through our veins and gleam in our jewelry. What makes this supernova special isn't just its age or its brilliance, but its role as a universe-shaping event. Back then, the cosmos was a simpler place, mostly filled with hydrogen and helium. This explosion was one of the first to seed space with the ingredients for planets, oceans, and even life itself. Astronomers studying its remnants, a faint, expanding bubble of gas and dust, can trace how these cataclysms acted as the universe's first factories, transforming primal matter into something richer, more complex. But here's the poetic twist: destruction birthing creation. That star's violent end didn't just vanish into darkness. It became the raw material for new stars, new worlds, and one day, creatures who would look up and wonder where it all began. Every time you see a glint of gold or feel the weight of a wedding ring, you're touching stardust forged in an explosion older than our solar system. The universe, it seems, has a way of recycling its tragedies into something beautiful, and this supernova's light, arriving now after eons of travel, is its way of reminding us, even in the vastness of space, nothing is ever truly lost. Now picture this: two stars bound together in an endless embrace, circling each other so closely that their gravity warps the very fabric of space around them. This isn't science fiction, it's the second story in our cosmic collection, a tale of celestial partners whose rhythmic dance has been playing out for billions of years before their light finally graced our telescopes. These aren't just any stars, they're a binary system, one so precise in its movements that it acts like a cosmic metronome, ticking with the regularity of a clockwork universe. What makes this pair extraordinary isn't just their longevity, but the way they bend reality itself. As they orbit, their immense gravity distorts space-time, creating ripples that subtly alter the path of their light. When these tiny shifts finally reached Earth, they became one of the most compelling validations of Einstein's theory of relativity. Think about that, a prediction made over a century ago, confirmed by Starlight, that began its journey when our planet was little more than molten rock. These stars don't just shine, they whisper secrets about the fundamental laws that govern everything from falling apples to orbiting planets. Yet there's another layer to their story. Binary systems like this challenge everything we thought we knew about how stars live and die. Conventional wisdom says massive stars burn bright and fast, ending in fiery supernova. But these two have defied the odds, spinning around each other for eons without tearing apart or exploding. Their longevity hints at mysteries we're only beginning to unravel, like how such delicate gravitational balances can persist for billions of years, or what happens when one finally exhausts its fuel. Will it collapse into a black hole, or will its partner keep it alive like a cosmic life support system? And here's the most mesmerizing part: their light pulses like a heartbeat. Every time one star passes in front of the other, their combined brightness dips in a predictable rhythm, creating a celestial strobe visible across the universe. It's as if they're sending signals not just through space but through time itself. For astronomers, these pulses are like reading the pages of a cosmic history book, each flicker revealing details about their size, temperature, and even the turbulent winds that whip between them. This dance isn't just beautiful, it's transformative. By studying these binary systems, we've learned that stars rarely live solitary lives. Most have companions, hidden partners that shape their destinies in ways we're only starting to comprehend. So the next time you look up at a single bright point in the night sky, remember, it might not be one star at all, but two, locked in an eternal waltz, their story written in gravity and light, finally reaching us after a journey older than time. Somewhere in the depths of space, two galaxies are locked in a gravitational embrace so slow, so gradual, that if we could watch it unfold, it would seem frozen in time. This is our third story, a cosmic dance of destruction and creation, where spiral arms stretch like taffy and newborn stars ignite in the chaos. The light reaching us now left these colliding galaxies when Earth was a world of single-celled organisms, carrying with it a glimpse of a future that awaits our own Milky Way. What makes this collision extraordinary isn't just its scale, but its paradox. From our vantage point, these galaxies appear twisted, warped, as if painted by an artist who smudged the edges. Yet within that chaos lies creation. The immense gravitational forces at work compress clouds of gas, triggering bursts of star formation so intense they outshine entire galaxies. These aren't just stars being born, they're the universe's way of recycling, taking the raw materials of two old galaxies and forging something new. And here's the humbling part: this is a preview of our own cosmic destiny. In about 4 billion years, the Milky Way and Andromeda will begin their own slow-motion merger, a tango that will last eons. The night sky as we know it will transform, with unfamiliar constellations and a brilliant haze of newborn stars. But don't worry, the distances between stars are so vast that actual collisions are rare. Instead, gravity will sculpt both galaxies into something entirely new, likely a featureless elliptical galaxy, a silent testament to the impermanence of even the grandest cosmic structures. Yet even in this distant future, some things will endure. The light from these merging galaxies captured by our telescopes today reminds us that the universe is in constant motion, rewriting itself on timescales beyond human comprehension. Every star you see tonight is part of a story that began long before us and will continue long after. These colliding galaxies are more than a spectacle. They're a message from the past, a mirror held up to our future, and proof that even in the vastness of space, nothing stays the same. Deep in the cosmic archives, a single point of light outshines everything around it, not a star, not a galaxy, but something far more extraordinary. This is our fourth story, a quasar so luminous, its brilliance rivals 1,000 galaxies combined. But what you're seeing isn't just raw power. It's a time capsule, a beam of light that left its source when the universe was a fraction of its current age. A wild frontier where black holes grew to staggering sizes and galaxies were still taking shape. At the heart of this quasar lies a supermassive black hole, a cosmic predator devouring matter at a rate so furious, it heats the surrounding gas to millions of degrees. The energy released in this feeding frenzy creates a beacon visible across the universe, cutting through the primordial fog of the early cosmos. Today, that light arrives at our telescopes like a message in a bottle, carrying clues about an era when the first supermassive black holes were forming, an epoch scientists once thought was too brief for such giants to exist. Here's what makes this quasar revolutionary. It shouldn't be there. According to older models, black holes this massive needed billions of years to grow. Yet this one defies logic, already fully formed when the universe was less than a tenth of its current age. Its existence forces us to rewrite the rules, suggesting that the early universe had shortcuts, cosmic fast food drives where black holes gorged themselves on dense clouds of gas or merged with others in violent collisions. But quasars aren't just about destruction. They're cosmic lighthouses, their light piercing through interstellar gas like a flashlight in fog. As this ancient beam traveled toward us, it passed through clouds of primordial hydrogen, absorbing specific wavelengths and leaving fingerprints in its spectrum. Astronomers decode these fingerprints like detectives analyzing a crime scene, reconstructing the conditions of the early universe, how quickly it expanded, how matter clumped together, even the temperature of space before the first stars ignited. And there's a haunting beauty to its timing. This quasar's light began its journey when Earth's continents were still barren rock, before life had even begun its experiments with single-celled organisms. It's been traveling all this time through the rise and fall of dinosaurs, the birth of human civilization, and now, finally, it lands in our telescopes not just as data, but as a bridge across time. We're not just observing the past, we're touching it, measuring it, and in doing so, uncovering secrets about how the universe grew up. This quasar story is a reminder that even the most violent phenomena can illuminate the darkest corners of our understanding. Its light, older than mountains, older than oceans, is still teaching us, proving that the universe's history isn't locked away in some distant vault, but streaming toward us every night, written in photons that took billions of years to arrive. And if we're patient, if we keep looking up, there are countless more stories like this one waiting to be read. Not all cosmic stories begin with blazing light. Some whisper in the faintest infrared glow, like our fifth tale of a lone wanderer. Imagine a planet untethered from any star, cast adrift in the endless black between galaxies. This isn't science fiction. It's a rogue planet, its faint heat signature only recently detected after billions of years of solitary travel. Unlike the planets in our solar system basking in the warmth of the sun, this exile drifts through freezing darkness, its surface colder than the deepest ocean trenches on Earth. Yet its very existence rewrites what we thought we knew about how planetary systems form and how often they fall apart. What makes this rogue planet extraordinary isn't just its loneliness, but its origin story. Astronomers believe it was likely born in a violent celestial neighborhood, where gravitational tugs from passing stars or sibling planets sent it careening into the void like a cosmic pinball. One moment it orbited a young star, the next it was flung into the abyss, destined to wander forever. The fact that we've spotted it at all is a testament to how sensitive our telescopes have become, catching the dim afterglow of a world that, by all rights, should be invisible. Here's the twist: rogue planets might outnumber stars in our galaxy. Current estimates suggest there could be billions of these nomads drifting unseen through interstellar space. Some may have thick atmospheres trapping residual heat, creating subsurface oceans where life could theoretically cling to existence, cut off from any starlight. Others might be barren ice balls, their surfaces scoured by cosmic rays over eons. Each one is a time capsule, preserving the conditions of its birth system like a fossil frozen in motion. But the real mystery lies in what they reveal about cosmic chaos. For every orderly system like ours, with planets orbiting in near-perfect alignment, there might be dozens where gravitational mayhem left survivors scattered. These rogue worlds hint at a universe far more dynamic and far less predictable than we once assumed. They're reminders that even the most stable-looking systems can be upended, that planets can be stolen, traded, or exiled in the gravitational interplay of stars. And then there's the haunting beauty of its journey. While stars and galaxies dominate our view of the cosmos, this planet tells a quieter story, one of resilience in isolation. Its light, if you can call it that, is barely a whisper, a testament to the countless unseen worlds moving through the darkness. The next time you look up at the night sky, remember, between those bright points of light, there are invisible travelers, each carrying tales of systems born, broken, and reborn. Their stories aren't written in starlight, but in the silent spaces between. Out in the cosmic darkness, a dead star spins faster than a kitchen blender, sending beams of radiation slicing through space like a lighthouse cutting through fog. This is our sixth story, a pulsar, the universe's most precise timekeeper. Born from the violent death of a massive star, this neutron star packs more mass than our sun into a sphere no wider than a city, spinning so fast its surface moves at nearly a quarter the speed of light. But what makes it extraordinary isn't just its dizzying rotation, it's the way its rhythmic pulses, traveling for millennia, now serve as both a cosmic clock and an interstellar GPS. Every pulse we detect is a heartbeat from a stellar corpse, a signal so regular it rivals atomic clocks on Earth. When these pulses finally reach us after their billion-year journey, they're more than just flashes of light, they're stress tests for Einstein's theories. As the beams pass through warped space-time near massive objects, their timing shifts in ways that reveal hidden planets, measure the fabric of the universe, and even hint at gravitational waves rippling through the cosmos. It's as if the universe handed us a tuning fork, and we're using it to listen for the subtle distortions in reality itself. Yet pulsars aren't just scientific tools, they are potential roadmaps for future explorers. NASA Voyager probes carry pulsar maps on their golden records, with instructions on how to locate Earth based on the unique timing of these cosmic beacons. Think about that. Civilizations thousands of years from now could triangulate our position in the galaxy using stars that died before humans walked the Earth. There's something profoundly hopeful about that, a message in a bottle made of starlight, waiting to guide travelers we'll never meet. And then there's the sheer endurance of these spinning marvels. Some pulsars have been ticking with metronomic precision for millions of years, outliving the civilizations that might have once observed them. Their beams, powered by magnetic fields trillions of times stronger than Earth's, sweep across the galaxy like searchlights, etching paths that will outlast mountain ranges, oceans, even continents. When we catch one of these pulsars, we're not just seeing a dead star, we're witnessing a cosmic legacy, a testament to the universe's ability to create order from chaos. What's most humbling is how these celestial lighthouses redefine time itself. The light from your average star tells a story of fusion and heat, but a pulsar's pulses are a story of rhythm, a beat that persists long after the music of its birth has faded. They remind us that even in death, stars can become something new, not just relics, but guides, timekeepers, and silent partners in our quest to understand the cosmos. So the next time you hear about a pulsar's steady blink, remember, you're not just observing a phenomenon, you're syncing your watch to a clock that's been running since before time had meaning. Every star has its final act, but few bow out with such breathtaking grace as the red giant in our seventh story. Imagine a celestial painter, its brushstrokes made of glowing gas, crafting a masterpiece so vast it could swallow our entire solar system. This is the planetary nebula, not a birthplace of planets, as its misleading name suggests, but the shimmering funeral shroud of a dying star. The light reaching us now began its journey when humans were first etching symbols into clay tablets, carrying with it a vision of stellar death transformed into art. What makes this nebula extraordinary isn't just its beauty, but the physics behind its delicate filaments and symmetrical shells. As the red giant exhausted its nuclear fuel, it pulsed like a failing heartbeat, shedding layers of gas at intervals. These ejected shells, illuminated by the dying star's ultraviolet radiation, now glow with ethereal hues: oxygen burning green, hydrogen blazing red, nitrogen flickering blue. But here's the twist: the nebula's intricate shapes aren't random. Hidden planets, survivors of the star's violent expansion, sculpt these patterns with their gravity, like invisible hands molding cosmic clay. This stellar afterlife also holds a profound lesson about renewal. The expelled gas, rich in carbon and other heavy elements, will eventually mix with interstellar clouds, becoming raw material for new stars, new planets, perhaps even new life. That diamond ring on your finger, its carbon atoms might have once floated in a nebula just like this one. The universe doesn't waste its tragedies, it repurposes them into tomorrow's possibilities. And there's haunting mystery in the details. Some planetary nebulae exhibit bizarre structures, twin jets, spiral patterns, even hourglass shapes that defy simple explanation. Astronomers now suspect magnetic fields or binary star companions play a role, turning these stellar farewells into cosmic detective stories. Each unusual curve or knot in the gas is a clue, waiting to reveal how stars engineer their own spectacular exits. But perhaps the most humbling thought is this: our sun will one day perform its own version of this dance. 5 billion years from now, it too will swell into a red giant, engulfing Mercury and Venus, possibly even Earth, before shedding its skin to form a nebula of its own. The light from that future event will someday reach distant galaxies, carrying our star's story to civilizations we can't yet imagine. These nebulae remind us that even in death, stars don't vanish, they transform, leaving behind not just ashes, but seeds for the next chapter of the cosmos. Somewhere in the cosmic void, Starlight bends without a visible hand, an eerie distortion that reveals the universe's best-kept secret. This is our 8th story, where galaxies spin too fast, light curves where nothing appears to be, and the very fabric of space-time bears the fingerprints of something we can't see. Dark matter, the universe's silent architect, doesn't glow, reflect, or absorb light, yet its gravitational grip shapes everything from the largest superclusters to the delicate dance of distant stars. The light arriving at our telescopes today tells a tale of an invisible force so pervasive, It outweighs all visible matter 5-1. What makes dark matter extraordinary isn't just its invisibility, but how it defies every expectation. When astronomers first noticed galaxies rotating faster than their visible mass could explain, they faced a cosmic puzzle. Either the laws of gravity were wrong, or most of the universe's mass was missing. The answer: a shadowy scaffold of matter woven through and between galaxies like an unseen skeleton. Its presence isn't just hinted at by math, it's etched into the sky. When light from distant stars arcs around seemingly empty space like a carousel horse veering off its path, we're witnessing dark matter's handiwork in real time. Here's where the mystery deepens. Dark matter doesn't behave like anything we know. It doesn't clump like normal matter. Instead, it forms vast, diffuse halos stretching far beyond a galaxy's luminous edges. Simulations show these halos should host countless subclumps, like invisible islands in an unseen sea. Yet telescopes find far fewer than predicted. Is dark matter smoother than we thought? Or are we missing a crucial piece of physics? The light carrying these clues has traveled so long. The universe itself was half its current age when the journey began. And then there's the tantalizing question: what is it? Theorists have proposed particles stranger than fiction. WIMP, weakly interacting massive particles, actions, even primordial black holes forged in the Big Bang's first seconds. Laboratories buried deep underground hunt for dark matter's faint whispers, while space telescopes map its cosmic distribution like cartographers of the invisible. Every failure to detect it directly only heightens the intrigue, suggesting we might need to rewrite physics itself. But dark matter's most profound legacy might be what it reveals about our place in the cosmos. The atoms making up planets, stars, and us, they're the rare exception, not the rule. Most of the universe is made of something utterly alien, a substance that passes through your body right now like a ghost through walls. The starlight we've relied on for millennia to tell the universe's stories only shows us a fraction of the truth. The rest is written in gravity's secret language, waiting for us to decipher it. So when you look up at the night sky, remember, the stars you see are just the tip of the iceberg. Behind them, beneath them, woven through the darkness, is the unseen architecture holding it all together. Dark matter isn't just a scientific problem, it's a cosmic riddle, a reminder that the universe, for all we've learned, still keeps its greatest secrets hidden in plain sight. Far beyond our solar system, a distant world orbits its star at just the right distance, not too close to boil its oceans away, not too far to freeze them solid. But how do we know this isn't just another barren rock? The answer lies in starlight itself, filtered through the planet's atmosphere like sunlight through a stained glass window. This is our ninth story, the silent language of exoplanet atmospheres, where molecules imprint their signatures on light that's traveled centuries to reach us. What might seem like a faint shift in color to our telescopes is actually a cosmic Rosetta Stone, revealing not just what these worlds are made of, but whether they could cradle life. Take a single beam of light passing through an exoplanet's air. As it does, atoms and molecules grab onto specific wavelengths like sticky fingers, leaving dark lines in the spectrum, a unique barcode for every chemical present. Water vapor might snag one wavelength, methane another, while oxygen leaves a telltale gap that sends astronomers' hearts racing. These aren't just data points, they're pages from an alien world's diary. One recent analysis of a planet 1,200 light-years away found swirling clouds of vaporized metals in its atmosphere, a world so hot it rains titanium. Another showed a puffy gas giant with an atmosphere so extended, its outer layers are literally boiling off into space like steam from a kettle. But the real magic happens when we find an atmosphere that looks familiar. Imagine detecting water vapor on a rocky planet in the habitable zone, a place where temperatures could allow liquid oceans, or spotting methane and oxygen together, a combination that on Earth only persists because life constantly replenishes it. These aren't just scientific discoveries, they're plot twists in humanity's greatest mystery. Are we alone? The light carrying these clues is older than the Great Pyramids, older than written language, yet it arrives now, just as we've developed the tools to read it. Here's what's astonishing. We're not just observing these atmospheres, we're beginning to map their weather. On one scorching hot Jupiter, winds scream at over 5,000 miles per hour, carrying clouds of molten silicate that glow like lava. Another world, tidally locked with one side always facing its star, might have a permanent hurricane raging at the boundary between eternal day and endless night. These aren't static snapshots, they're dynamic portraits of alien meteorology, painted by starlight that's been stretched, squeezed, and dissected by the planet's turbulent skies. Yet the most profound revelation might be how common atmospheres are turning out to be. From thick Venus-like shrouds to thin Martian hazes, exoplanets have shown us that our solar system's variety is just the tip of the cosmic iceberg. Some atmospheres are being born right now, outgassing from young planets like the early Earth's volcanic fumes. Others are slowly bleeding into space, their lighter elements stripped away by stellar winds. Each one tells a story of planetary evolution and, by extension, our own world's past and future. What's humbling is the patience required to read these stories. The light from one transit, a single dip in a star's brightness as the planet crosses, might last hours, yet carry just a whisper of atmospheric data. Astronomers must watch dozens, sometimes hundreds of these transits to tease out the spectral fingerprints. It's like trying to identify a perfume by smelling the air in a room someone passed through days ago. But with next-generation telescopes, we're on the verge of studying Earth-sized worlds with similar precision, potentially spotting the atmospheric signatures of forests, algae, or even industrial pollution. So the next time you see a pinprick of light in the night sky, consider this. Among those stars are planets with skies of every color, storms that would dwarf our hurricanes, and air that just might carry the faint, telltale signs of another civilization looking back at us across the light years. The universe has been writing these atmospheric memoirs for billions of years. We've only just learned how to read them, stretching across the cosmos like the veins of some colossal organism. An almost invisible network of glowing hydrogen connects everything we see in the night sky. This is our 10th story, the cosmic web, a blueprint of the universe written in the faintest ultraviolet glow, light so ancient it carries memories from a time before galaxies even existed. What appears as empty blackness between stars is actually a bustling highway of matter, with galaxies strung along filaments like pearls on a necklace, each thread pulsing with the afterglow of creation itself. The magic lies in how this web formed. In the early universe, tiny quantum fluctuations, random ripples in the fabric of space-time, grew under gravity's relentless pull. Dense regions attracted more matter, while emptier spaces stretched into vast voids. Over billions of years, this cosmic tug of war sculpted the web's delicate structure, with hydrogen gas flowing along its strands like water through riverbeds. Today, the light from this gas finally reaches us, revealing a pattern so vast, it takes supercomputers to map its full complexity. But here's the astonishing part. This isn't just a snapshot of the past. The cosmic web is alive with motion. Galaxies ride these filaments like surfers on waves, sliding toward intersections where clusters form. Some strands glow brighter where collisions heat the gas to millions of degrees, while others fade into near darkness, their hydrogen too diffused to emit much light. Yet even these dim threads hold secret traces of the universe's first elements. forged in the hearts of long-dead stars and scattered across the web by supernova winds. What's truly humbling is the scale. A single filament can stretch hundreds of millions of light years, linking thousands of galaxies in a gravitational embrace. Zoom out far enough, and the entire universe resolves into this intricate lacework, with voids so large they could swallow thousands of Milky Ways without touching the sides. It's a structure so grand, it redefines our sense of place. Earth isn't just orbiting a star in a galaxy. We're perched on one thread of an unimaginably vast tapestry. And then there's the light itself. This hydrogen glow, called the Lyman Alpha Forest, isn't just pretty, it's a time machine. By analyzing how the web's light has been absorbed and redirected during its journey, astronomers can reconstruct how the universe expanded, how dark matter shaped it, even how the first black holes flooded space with radiation. Each faint photon is a messenger carrying clues about epochs when the cosmos was raw and uncharted. Perhaps most mind-bending of all, we're inside the web right now. The Milky Way sits on a filament, part of the local sheet, a flat structure of galaxies that feels like solid ground until you realize it's just one flake in a snowstorm of similar formations. Every time you gaze at the night sky, you're looking out through this network, seeing distant galaxies whose light has traveled along the web's highways to reach your eyes. The cosmic web doesn't just connect galaxies, it connects us to the universe's deepest history. Its filaments are the brushstrokes of gravity's masterpiece, a work still in progress, still expanding, still writing the next chapter of the cosmos. And the light arriving now, after traveling since the universe's youth, is our front row seat to watch it unfold. Trillions of nearly invisible particles pass through your body every second, leaving no trace, no heat, no light, no sensation. These are neutrinos, the universe's most elusive messengers, born in the nuclear furnaces of stars and the explosive deaths of supernova. Unlike light, which can be scattered, absorbed, or bent by interstellar dust and gravity, neutrinos travel in near-perfect straight lines, piercing planets, stars, even entire galaxies as if they weren't there. The neutrinos hitting Earth right now might have come from a star that died before our solar system formed, carrying a story so pristine, it's untouched by the chaos of the cosmos. Detecting these cosmic ghosts is like trying to catch smoke with your bare hands. Most neutrinos will sail through a light year of solid lead without a single interaction. Yet scientists have devised extraordinary traps to snare the occasional one that does collide with matter. Deep underground, in tanks filled with ultra-pure water or liquid argon, detectors wait in perfect darkness. When a neutrino finally strikes an atomic nucleus, it creates a faint flash of light or a ripple of charged particles, a signal so rare and delicate, it's often drowned out by background radiation from rocks or even bananas. The fact that we've captured any at all is a triumph of human ingenuity. What makes neutrinos revolutionary isn't just their stealth, but their honesty. Light from a supernova can be distorted by gas clouds or dimmed by dust, but neutrinos arrive unaltered, delivering a pure timestamp of the explosion's core. When the famous supernova 1987 lit up the sky, neutrino detectors on Earth registered 24 of these particles hours before the visible light reached us. Proof that while photons dawdle through the star's outer layers, neutrinos burst out at nearly the speed of light, unimpeded. They're the universe's emergency broadcast system, signaling catastrophe in real time. Yet neutrinos hold deeper mysteries. They come in 3 flavors: electron, muon, and tau, and can shapeshift between them mid-flight, a quantum quirk called oscillation. This chameleon behavior proved that neutrinos, long thought to be massless, actually have a tiny weight, a discovery that upended particle physics. Now, scientists suspect these particles might hold clues to why the universe is made of matter at all. In the Big Bang's aftermath, matter and antimatter should have annihilated each other perfectly. That we exist suggests a slight asymmetry in nature's laws, and neutrinos, with their eerie ability to defy expectations, might be the key to solving this existential riddle. The most poetic part, neutrinos connect you directly to the cosmos's most violent events. Some passing through you now were forged in the sun's core 8 minutes ago, while others are relics of ancient supernova, their journeys spanning millennia. They're the universe's whispering network, carrying secrets from places light can't escape, like the heart of a collapsing star or the swirling disk of a black hole. Every time a neutrino detector flashes, it's not just recording a particle, it's intercepting a love letter from the universe's most hidden corners, written in a language we're only beginning to decode. So the next time you stand under the night sky, remember, you're not just an observer of the cosmos, you're a living neutrino detector, bathed in particles older than civilization, bearing silent witness to the universe's most explosive dramas. They remind us that even the smallest, quietest things can carry the grandest stories, if we're patient enough to listen. At the heart of the galaxy Messier 87, an unthinkable darkness swirls a black hole so massive, its gravity bends light itself into a fiery halo. This is the story behind humanity's first glimpse of a black hole's shadow, an image that transformed theoretical physics into something visceral, almost touchable. The light forming that iconic orange ring began its journey 55 million years ago, when Earth was a world of rainforests and early primates. By the time it reached our telescopes, it carried not just proof of Einstein's genius, but a front-row seat to spacetime's most extreme demolition derby. What makes this shadow revolutionary isn't just its existence, but its imperfections. The ring isn't uniform, it's brighter on one side, a telltale sign of the black hole's dizzying spin. Like water spiraling down a drain, the accretion disk of superheated gas orbits at nearly light speed, its particles colliding so violently they glow with the energy of 1 trillion suns. The brighter edge, that's gas moving toward us, its light amplified by relativistic beaming, a cosmic version of a train whistle sounding higher pitched as it approaches. The dimmer side, gas fleeing our view, its light stretched and dimmed by the same physics. Together, they paint a portrait of chaos choreographed by gravity's unbreakable rules. But the real magic lies in how we captured it. The Event Horizon Telescope wasn't a single instrument, but a planet-sized virtual observatory linking dishes from the South Pole to the Spanish Highlands. Synchronized by atomic clocks, they collected data so vast it couldn't be sent over the internet. Hard drives had to be flown to supercomputers for analysis. The result, an image with resolution sharp enough to read a newspaper on the moon from Earth, teasing out details smaller than the black hole's event horizon. That faint glow isn't just artistic license, it's the last stand of photons trapped in orbit, a cosmic ballet of light dancing on the edge of oblivion. Hidden in that asymmetry is a clue to the black hole's origin story. The direction and tilt of its spin suggest a violent past, perhaps a collision with another black hole, a gravitational shockwave that sent it spinning like a top. Some theories even suggest the spin could warp spacetime around it into a whirlpool shape, a phenomenon straight out of science fiction. Yet for all its power, this monster is strangely orderly. The neatness of its shadow confirms Einstein's predictions with uncanny precision, proving that even in the universe's most chaotic environments, relativity holds sway. What's haunting is how temporary this spectacle really is. Given enough time, even black holes evaporate, leaking energy through quantum processes until they vanish in a final burst of radiation. The shadow we see today is just a snapshot in a cosmic lifespan spanning trillions of years. But for now, it stands as a beacon, a reminder that the universe's most enigmatic objects aren't hiding. They're broadcasting their secrets across the ages, if we're bold enough to look into the darkness and decode what stares back. In the blink of a cosmic eye, a single gamma-ray burst can release more energy than our Sun will emit in its entire 10-billion-year lifetime. This is the universe's most violent farewell, a death cry so powerful, its light outshines every star in its host galaxy combined. The 13th story in our celestial anthology begins with such a cataclysm, a beam of high-energy radiation so intense, it slices across the cosmos like a scalpel through fabric. By the time its fading afterglow reaches Earth, often decades or even centuries after the initial explosion, it carries forensic evidence of what triggered it: the collapse of a massive star into a black hole, or the apocalyptic collision of two neutron stars. What makes these bursts so extraordinary isn't just their power, but their duality. They're both destroyers and creators. Within their relativistic jets, particles accelerate to nearly the speed of light, creating conditions so extreme they forge heavy elements like gold, platinum, and uranium, the very same metals that glitter in jewelry and power nuclear reactors. A single gamma-ray burst might be the universe's ultimate alchemist, transforming the corpses of dead stars into the building blocks of future worlds. Yet that same beam, if pointed at a planet like Earth, could strip away its ozone layer in seconds, bathing its surface in lethal radiation. Some scientists suspect one of these bursts, occurring within a few thousand light-years, might have triggered mass extinctions in our planet's past. The irony is poetic. These explosions, capable of sterilizing entire solar systems, also sprinkle the cosmos with the ingredients for life. The gold in your wedding ring, the uranium fueling reactors, even the iodine in your thyroid, all were likely born in the heart of a gamma-ray burst or its aftermath. It's as if the universe balances its scales with ruthless precision. To create, it must first destroy. Detecting these bursts is like catching lightning in a bottle. Lasting anywhere from milliseconds to several minutes, they appear randomly across the sky, vanishing before telescopes can swivel into position. That's where the afterglow becomes crucial. As the jet slams into interstellar gas, it creates a lingering echo of X-rays, visible light, and radio waves, a cosmic crime scene that astronomers scour for clues. The color and fade rate of this afterglow reveal the burst's distance, energy, and even the density of the material it's plowing through. One recent burst, catalogued as GRB 2,022,1916A, was so bright it temporarily blinded satellites, and its afterglow showed traces of newly forged heavy elements, confirming these events as cosmic foundries. But the real mystery lies in what we don't see. Some bursts leave no afterglow at all, suggesting their jets were pointed directly at Earth like a flashlight beam, a scenario called a naked burst. Others emit faint, erratic glows, hinting at chaotic environments where black holes binge on surrounding matter. The rarest bursts, lasting less than 2 seconds, likely signal the merger of neutron stars, events so violent they ripple space-time itself, producing gravitational waves detectable across the universe. What's humbling is the timing. The light from these bursts often crosses paths with civilizations that rise and fall before it arrives. A gamma-ray burst observed in 2023, for instance, may have actually occurred when the Roman Empire ruled Europe, its light only now reaching us after a 2,000-year journey. And somewhere out there, another burst's light is already en route, carrying news of a catastrophe that hasn't yet happened from our perspective. These bursts remind us that the cosmos operates on a scale beyond human intuition. Events lasting seconds can shape galaxies for eons, and death on one world might mean life for another. The universe writes its stories in extremes, and gamma-ray bursts are its boldest punctuation, exclamation points carved into the fabric of spacetime, visible long after the ink has dried. Stretching across the entire sky like a faded tattoo from the universe's birth, there's a glow so cold it hides in plain sight the cosmic microwave background. This isn't just ancient light, it's the afterglow of creation itself, a relic from when the cosmos was a seething plasma of particles and energy, barely 380,000 years old. Today, that primordial fire has cooled to just 2.7 degrees above absolute zero, its brilliance diluted by 14 billion years of cosmic expansion into faint microwaves. Yet hidden within this whisper-thin radiation lies the universe's baby picture, a snapshot of its infancy encoded in temperature variations smaller than 1/100th of a degree. What makes this glow extraordinary isn't just its age, but its imperfections. Those tiny fluctuations, some slightly warmer patches, others cooler, are the universe's first brushstrokes, the gravitational seeds from which galaxies, stars, and eventually planets would sprout. Imagine tossing pebbles into a pond. The ripples they create might seem random at first, but trace them backward, and you'll find the exact moment each stone hit the water. The cosmic microwave background works the same way. By mapping its subtle patterns, astronomers can rewind the universe's expansion to its very first trillionth of a second, revealing how quantum jitters in the newborn cosmos were stretched by inflation into the large-scale structures we see today. But the real magic lies in what this light confirms about the universe's shape. The geometry of spacetime isn't just an abstract concept, it's written in the size and spacing of those temperature variations. If the cosmos were curved like a saddle, distant patches would appear smaller. If it were closed like a sphere, they'd loom larger. Instead, the cosmic microwave background reveals a universe so flat, it suggests our visible cosmos is just a tiny fraction of something far grander, perhaps infinite. It's as if we've spent centuries studying a single grain of sand, only to realize we're standing on an endless beach, and then there's the haunting echo of sound. In those first fiery moments, the universe wasn't silent. It was a roaring ocean of pressure waves, with regions of dense plasma collapsing and rebounding like cosmic drumheads. These oscillations left their mark on the microwave background as alternating rings of slightly hotter and cooler gas, a fingerprint that lets astronomers calculate the universe's composition with razor precision. The result, a cosmic recipe of 5% ordinary matter, 27% dark matter, and 68% dark energy, numbers that still keep physicists awake at night, wondering what most of reality is truly made of. Here's the twist: we're not just observing this light, we're swimming in it. Every time you tune an old analog television to static, about 1% of that snow comes from photons emitted during the universe's toddler phase. The same is true for the faint hiss between radio stations or the glow of an empty microwave oven, though your leftovers heat up from much more recent waves. This radiation is so pervasive, it's literally the baseline of existence, the oldest thing any human will ever perceive. Yet the cosmic microwave background isn't just a museum piece. It's still evolving. As the universe expands, these microwaves stretch further, their wavelengths growing longer and their energy fading. Billions of years from now, they'll redshift into radio waves, then eventually become undetectable altogether, erasing the last visible trace of the Big Bang. That we exist in the brief cosmic moment when this light is still observable feels like a gift, a chance to touch the universe's origins before the curtain falls. So the next time you glance at the static on a dead channel, remember, you're not just seeing noise, you're glimpsing the afterimage of creation, a message from a time when everything, every atom, every galaxy, every possibility was compressed into a singularity smaller than a grapefruit. The cosmic microwave background doesn't just tell us where we came from. It's a reminder that the universe, for all its vastness, still carries the scars of its explosive birth. And those scars, faded as they are, light the way to understanding everything. The faintest chirp, barely louder than the hum of background noise, can rewrite our understanding of the cosmos. This is the story of gravitational waves, ripples in the fabric of spacetime itself, born from the most violent mergers in the universe. Picture two black holes, each heavier than 30 suns, locked in a death spiral. As they orbit faster and faster, they warp spacetime like a spinning dancer twisting a sheet, sending out waves that travel at light speed across billions of years. By the time these tremors reach Earth, they've faded to near silence, stretching and squeezing our planet by less than the width of an atomic nucleus. Yet in 2015, humanity's most sensitive machines caught one of these whispers, proving Einstein right in a way he never thought possible. What makes these detections extraordinary isn't just their confirmation of relativity, but the stories they tell. Each chirp, a rapid rise in pitch followed by sudden silence, is a cosmic fingerprint. The duration, frequency, and amplitude reveal the black hole's masses, spins, and even how long they danced before colliding. Some signals last mere milliseconds, the hallmark of lightweight black holes merging swiftly. Others, like the historic GW1509, stretch for seconds, tracing the final agonizing orbits of giants before they became one. The moment of collision itself is violent beyond comprehension, converting 3 solar masses of matter into pure energy in a fraction of a second, a burst of gravitational waves briefly outshining every star in the observable universe combined. But the real magic lies in how we listen. Gravitational wave observatories like LIGO and Virgo are arguably the quietest places on Earth. Their laser beams, traveling down 4-kilometer vacuum tubes, detect disturbances smaller than a proton. When a wave passes, it subtly alters the laser's path lengths, creating an interference pattern that translates spacetime's shiver into sound. The result: a chirp so pristine you can hear the universe's curvature in its rising tone. It's as if spacetime itself is singing, and after 14 billion years, we've finally tuned in. These waves also solve an astronomical blind spot. Black holes, by definition, emit no light, yet their mergers flood the cosmos with gravitational ripples. Before 2015, we could only infer their existence through their effects on visible matter. Now, we're eavesdropping on their private lives, learning that binary black holes might be far more common than models predicted. Some detections suggest black holes spin at dizzying rates, their event horizons whipping around at nearly light speed. Others hint at hierarchical mergers, smaller black holes colliding to form mid-size ones, which then merge again like cosmic matryoshka dolls. Perhaps most astonishing is how little these waves care about the universe's clutter. Light gets absorbed, refracted, or scattered by dust and gas, but gravitational waves pass through everything: galaxies, neutron stars, even other black holes, utterly unfazed. A wave detected today might have traveled through a supernova's heart, skirted the edge of a quasar, or slipped between the atoms of a dinosaur's bones, all without a single deflection. They're the universe's most faithful messengers, delivering news from the darkest corners unchanged, and the symphony is growing richer. With each new detection, we're compiling a catalog of cosmic collisions, not just black holes, but neutron stars, white dwarfs, and possibly even exotic objects we've yet to name. The merger of 2 neutron stars in 2017, dubbed GW170817, was a Rosetta Stone event. Its gravitational waves arrived first, followed seconds later by gamma rays, then a rainbow of visible light, X-rays, and radio waves, a multi-messenger bonanza that confirmed neutron star mergers as factories for gold and platinum. Suddenly, gravitational astronomy wasn't just about testing theories. It was about tracing the origin of the elements in your smartphone. What's humbling is the scale of these conversations. The black holes that created GW1509 likely merged when life on Earth was limited to single-celled organisms. Their waves spent 1.3 billion years crossing intergalactic space, passing through countless civilizations that rose and fell, only to be captured by a species that hadn't yet evolved opposable thumbs when the signal began its journey. And somewhere out there, another ripple is already en route, carrying news of a collision that hasn't happened yet from our perspective, a future echo waiting to rewrite our textbooks. Gravitational waves remind us that the universe speaks in more than light. It thrums with vibrations, a cosmic drumhead resonating with every cataclysm. With each new chirp, we're not just hearing the universe, we're feeling its heartbeat, tracing the invisible architecture that holds it all together. And this is just the beginning. One day in 2017, astronomers spotted something strange, a visitor moving too fast to be bound by our sun's gravity, tumbling through the solar system on a trajectory that could only mean one thing: it came from another star. This was Oumuamua, the first known interstellar comet, a silent traveler from depths of space so distant, its home system remains a mystery. Its arrival was like finding a message in a bottle washed up on a beach, except the bottle was a quarter-mile-long rock, tumbling end over end, and the beach was the void between worlds. What made Oumuamua extraordinary wasn't just its origin, but its strangeness. Unlike most comets, it showed no visible tail of gas or dust as it neared the sun. Its shape, inferred from brightness variations, was bizarrely elongated, perhaps 10 times as long as it was wide, like a cosmic cigar or a pancake flipped edgewise. Some scientists suggested it might be a fragment of a shattered planet, sheared off by a catastrophic collision in some faraway system. Others, controversially, floated the idea of artificial origins, though most astronomers agree its behavior fits natural explanations, just ones we haven't seen before. The truth is, Oumuamua defied easy classification, a reminder that the universe specializes in surprises. Then there's the mystery of its acceleration. As Oumuamua sped away from the sun, it didn't follow the precise path gravity alone would dictate. It sped up slightly, as if pushed by some unseen force. Comets often exhibit this due to outgassing sun-heated ice boiling off and acting like a thruster. But no such gas was detected. Hypotheses range from hidden hydrogen ice vaporizing in sunlight to the release of trapped, exotic ices we've never encountered. Or perhaps its dust was unusually fine, invisible to telescopes but enough to nudge it along. Whatever the answer, Oumuamua's odd behavior suggests the chemistry of other star systems might operate by rules we're only beginning to glimpse. What's haunting is how fleeting its visit was. From discovery to fading beyond detection took mere weeks, far too brief to study in depth. By the time telescopes swung toward it, Oumuamua was already racing away, carrying untold secrets back into the dark. Its speed means it's likely spent millions of years drifting between stars before encountering our sun, and it'll likely wander for millions more before another star captures or alters it. That we noticed it at all was pure cosmic luck, a testament to how much of the universe's traffic slips by unseen. Yet Oumuamua was just the beginning. In 2019, another interstellar visitor comet Borisov arrived, this one trailing a familiar-looking tail of gas and dust. Unlike Oumuamua, Borisov resembled local comets, suggesting that while some interstellar objects might be bizarre, others could be strikingly familiar. Together, they hint at a galactic ecosystem richer than we imagined, where trillions of icy bodies crisscross the void, carrying material between star systems like bees pollinating flowers. Some might even transport the raw ingredients for life, seeding planets with water or organic molecules from distant worlds. These interstellar nomads raise profound questions. Did Oumuamua's home system have planets? Were they rocky like Earth or gas giants like Jupiter? Was there ever life there, or is it sterile? We'll likely never know, but that's what makes these visitors so tantalizing. They're postcards from places we'll never see, written in geology and ice, reminding us that our solar system isn't an island. It's part of a vast, interconnected network, where even the smallest rocks can cross light years, carrying stories older than human civilization. The next time you look up at the night sky, consider this. Right now, countless objects like Oumuamua are drifting unseen through the solar system, silent witnesses to the galaxy's grand history. Most will pass through unnoticed, but a few, like our first interstellar guest, will blaze briefly into view long enough to remind us that the universe is far stranger and far more connected than we ever dreamed. Some stars don't fade quietly, they leave behind ticking time bombs of pure cosmic terror. Meet the magnetar, a neutron star so magnetically charged, its mere existence defies physics. Imagine crushing the sun's mass into a sphere smaller than Manhattan, spinning it faster than a blender blade, then wrapping it in a magnetic field a quadrillion times stronger than Earth's. The result, a celestial powder keg where the crust is under such unimaginable strain. It occasionally cracks like a cosmic eggshell, releasing bursts of energy so violent they'd sterilize planets light years away. The deadliest flare ever recorded came from a magnetar 50,000 light years away, yet in 2004, its gamma-ray pulse still managed to briefly ionize Earth's upper atmosphere. If that same outburst had occurred within 10 light years of us, it could have triggered a mass extinction by stripping away our ozone layer in seconds. What's terrifying isn't just the power, it's the unpredictability. Unlike pulsars with their metronomic ticks, magnetars erupt without warning. They're starquakes launching tsunamis of X-rays and gamma rays across the galaxy. One theory suggests these quakes occur when the star's impossibly rigid crust fractures under magnetic stress, releasing pent-up energy like a coiled spring suddenly snapping. Yet magnetars also hold clues to the universe's most energetic mysteries. Their magnetic fields so intense they distort the quantum vacuum itself may be the engines behind some fast radio bursts, those enigmatic cosmic sirens we've detected from distant galaxies. The magnetic decay powering these stars is so extreme that over a mere 10,000 years, a blink in cosmic terms, a magnetar's field weakens into oblivion, leaving behind an ordinary neutron star. We're essentially catching these monsters in their brief, hyperactive adolescence before they burn out. Here's where the story takes an eerie turn. The light from most known magnetar flares has been traveling for centuries, meaning some of these eruptions actually occurred when Galileo was first pointing telescopes skyward, or when medieval astronomers recorded guest stars they couldn't explain. There might be magnetar flares whose light is already en route to Earth, their lethal energy racing toward us at light speed, utterly invisible until the moment they strike our atmosphere. But magnetars aren't just agents of destruction. Their extreme environments are natural laboratories for testing physics under conditions no Earth experiment could replicate. Quantum electrodynamics predicts bizarre effects near their surfaces, like light bending at right angles or particles materializing spontaneously from the vacuum. Some researchers even speculate that certain magnetars could power theoretical stargates, regions where space-time is so warped, shortcuts through the cosmos might briefly form. What makes these objects truly humbling is their duality. They're both destroyers and illuminators, capable of sterilizing entire star systems while simultaneously revealing the fundamental laws governing our universe. Their flares are cosmic alarm bells, reminding us that the serene night sky is an illusion, a temporary calm, in a universe teeming with forces beyond our control. The next time you gaze at the Milky Way, remember, somewhere in that glittering band, a magnetar may be winding its magnetic spring, storing energy for an eruption that will one day light up the galaxy, a message from the future written in violence. Most stars won't explode in a blaze of glory or collapse into black holes. They'll fade into a state of celestial retirement, crystallizing into Earth-sized diamonds that glow faintly against the cosmic dark. These are white dwarfs, the universe's stellar fossils, and their slow, quiet deaths tell a story more profound than any supernova. Imagine the core of a star like our Sun, stripped of its outer layers and compressed until a teaspoon of its material weighs as much as an elephant. What remains isn't just a cooling ember, it's a time capsule, preserving a record of the star's life and the elemental alchemy that unfolded in its core. The magic lies in how these remnants form. When a star exhausts its nuclear fuel, it sheds its outer atmosphere in a shimmering planetary nebula, leaving behind an exposed core of carbon and oxygen, ash from billions of years of fusion. But without the outward pressure of nuclear reactions, gravity crushes this core into a sphere so dense, electrons are jammed shoulder to shoulder in a state called degenerate matter. The result, a star corpse so hot it initially shines with the brilliance of a small sun, but with no energy source left, it can only cool slowly, relentlessly, over trillions of years. Yet cooling doesn't mean stillness. As a white dwarf ages, something extraordinary happens. Its core begins to crystallize. Yes, you heard that right, it turns into a diamond. Not the glittering gemstones we know, but a lattice of carbon atoms locking into place as the star's internal temperature drops. This process isn't quick. It takes billions of years for the first crystals to form, and by the time the dwarf fully solidifies, the universe might be so old that new stars no longer ignite. That faint glow we detect today, it's the last heat of a star's youth, radiating into space long after the star itself has ceased to be. What makes white dwarfs revolutionary isn't just their fate, but their composition. They're cosmic recycling plants. The carbon and oxygen in their cores were forged during the star's lifetime, then left behind like ingredients in a cosmic pantry. When these dwarfs eventually cool into black dwarfs, hypothetical objects so cold they emit no light, their material will remain locked away, waiting for a future supernova or collision to scatter them back into the interstellar medium. The calcium in your bones, the oxygen in your lungs, even the carbon in every living thing, much of it passed through a white dwarf's ancestor long before Earth existed. But here's the haunting twist. White dwarfs aren't always peaceful. Some, especially those with close companion stars, can steal material from their neighbors until they cross a critical threshold, the Chandrasekhar limit. When that happens, the dwarf detonates in a Type Ia supernova, an explosion so uniform in brightness that astronomers use it as a standard candle to measure cosmic distances. These blasts are rare, but when they occur, they seed the galaxy with iron, silicon, and other heavy elements, the very stuff of rocky planets like ours. The most mesmerizing part, white dwarfs are patient. The oldest ones we've found are nearly as ancient as the universe itself, their light reddened and dimmed by eons of cooling. They're the tombstones of the first stellar generations, silent witnesses to cosmic history, and in their spectra, the fingerprints of light they emit, we can read the story of their birth, life, and death. Traces of hydrogen or helium might reveal how much of their outer layers they lost. Unexpected metals could hint at planets they consumed in their death throes. Each one is a forensic record waiting to be decoded, so the next time you look up at the night sky, remember, among those glittering points are stars that will one day join this quiet retirement. Our own sun, 5 billion years from now, will shrink into a white dwarf no larger than Earth, its brilliance fading over ages longer than all of human history. But in that fading lies a promise, a reminder that even in death, stars don't vanish. They transform, leaving behind diamonds in the dark, each one a monument to the universe's endless cycle of creation and rebirth. Some stars don't just drift through the cosmos, they're catapulted into the void like cosmic cannonballs, fleeing their home galaxies at speeds that defy imagination. This is the story of hypervelocity stars, stellar fugitives flung into the abyss by gravitational forces so extreme, they make black holes look like playground swings. Picture a star once peacefully orbiting the center of its galaxy, suddenly whipped into motion by the gravitational slingshot of a supermassive black hole. The acceleration is so violent, the star breaks free entirely, streaking through intergalactic space at over 1 million miles per hour, fast enough to cross the distance between New York and Los Angeles in less than 10 seconds. What makes these stars extraordinary isn't just their speed, but their origin story. Tracing their paths backward leads astronomers straight to the hearts of galaxies, where supermassive black holes lurk like monstrous gatekeepers. When a binary star system wanders too close, one star might be captured in a deadly orbit while the other is ejected at blistering velocity, like a stone from a sling. The energy required to achieve this escape is staggering, equivalent to the force of 1,000 supernovae, yet black holes wield it casually, reshaping their surroundings with gravitational might. These runaway stars aren't just curiosities, they're cosmic breadcrumbs revealing secrets about the environments that spawned them. By studying their composition, scientists can reconstruct the chemical makeup of their home galaxies, even if those galaxies are too distant or dim to observe directly. Some hypervelocity stars carry traces of rare elements, suggesting they originated in chaotic, metal-rich regions near galactic cores. Others, surprisingly, seem too young for their projected journeys, hinting at violent star-forming bursts triggered by black hole activity. Then there's the haunting beauty of their solitude. Unlike most stars which live and die within the bustling communities of galaxies, hypervelocity stars are destined to wander the void alone. Over billions of years, they'll drift between galaxies, their light fading into the darkness, untouched by the gravitational pull of any celestial structure. Some might eventually be captured by another galaxy, but most will continue their endless journey, becoming ghosts of a home they'll never see again. Yet even in their exile, these stars serve a purpose. Their trajectories act as probes, mapping the distribution of dark matter in intergalactic space. As they speed through unseen halos of mysterious mass, subtle tugs on their paths reveal where and how dark matter clusters, a celestial game of pin the tail on the donkey played across millions of light years. What's most humbling is the timescale. The hypervelocity star you're hearing about today might have been ejected when the first fish crawled onto land, its light only now reaching us after an eons-long journey. And somewhere out there, another star is being flung into the abyss right now, its great escape already underway, though its light won't arrive for millennia. These stellar outcasts remind us that the universe isn't just a static backdrop, it's a dynamic arena of gravitational chaos, where even the seemingly permanent can be uprooted in an instant. So the next time you gaze at the night sky, remember, among those steady points of light, there are unseen travelers racing toward the unknown, carrying stories of forces powerful enough to defy galaxies. In the late 1990s, astronomers made a discovery so startling, it turned our understanding of the universe upside down. By studying distant supernova exploding stars that serve as cosmic mile markers, they noticed something bizarre. These stellar explosions weren't just far away, they were fainter than they should have been, as if something were stretching the very fabric of space between us and them. The implications were staggering. The universe wasn't just expanding, as Edwin Hubble had shown decades earlier. It was accelerating, its galaxies fleeing from one another faster and faster with each passing moment. And the force behind this runaway expansion, a mysterious, invisible presence we now call dark energy. What makes dark energy extraordinary isn't just its dominance. It makes up roughly 68% of the cosmos, but how little we understand it. Unlike gravity, which pulls matter together, dark energy behaves like an anti-gravity force pushing space-time apart. Imagine blowing up a balloon with dots on its surface. As the balloon expands, the dots move away from each other. Now imagine the balloon starts inflating faster, as if some unseen hand were pumping air into it at an ever-increasing rate. That's the effect dark energy has on our universe. The most perplexing part, unlike matter or radiation, its density doesn't dilute as space expands. It remains constant, meaning its influence grows as the universe gets bigger, ensuring acceleration will continue indefinitely. This discovery upended centuries of cosmic forecasting. Before dark energy, scientists debated whether the universe would expand forever at a steady pace, slow to a halt, or eventually collapse in a big crunch. Now the outlook is far stranger. If acceleration continues unchecked, distant galaxies will eventually recede so fast their light will never reach us, leaving future astronomers with a sky devoid of anything beyond our local galactic cluster. The universe won't end with fire or ice, but with isolation, a lonely, fading ember in an ever-darkening expanse. Yet dark energy's fingerprints aren't just in the future, they're etched into the universe's very structure. The cosmic microwave background, the afterglow of the Big Bang, reveals subtle patterns that only make sense if dark energy has been shaping spacetime for billions of years. Even the distribution of galaxies, with vast voids between filamentary structures, bears the mark of this relentless push. It's as if the cosmos is a tapestry, and dark energy is the invisible hand tugging at its threads, stretching it thinner with each passing eon. Theories about dark energy's nature range from the cosmological constant, a fixed energy density woven into spacetime itself, to dynamic fields that change over time. Some even suggest it's a sign of extra dimensions or a flaw in Einstein's equations, but every attempt to pin it down leads to more questions. Why does dark energy's strength appear fine-tuned to allow galaxies, stars, and life to exist? Is it truly constant, or could it evolve, potentially tearing atoms apart in a far future Big Rip? The light from those distant supernovae, after traveling billions of years, hasn't just illuminated the universe's expansion, it's exposed how much we still don't know. What's humbling is the timing. Dark energy's effects were negligible in the universe's youth when matter's gravity dominated. It's only in the last 5 billion years, around the time Earth formed, that it began steering cosmic destiny. We live in the brief epoch where both galaxies and dark energy's influence are visible, like witnesses to a passing of the torch. Future civilizations, if they arise, will gaze into a sky where most galaxies have vanished beyond an unreachable horizon, their histories erased by expansion. The light reaching us now is a fleeting gift, a chance to study a cosmos still rich with connections. Dark energy isn't just a scientific puzzle, it's a mirror held up to our place in the universe. Its discovery reminds us that reality is far stranger than we imagined, that the cosmos operates by rules we've only begun to decipher. And as those distant supernovae fade into obscurity, they leave behind a question as profound as any in science. What else is out there, hidden in the darkness, shaping the universe in ways we can't yet see? Around a fledgling star, barely 1 million years old, a swirling disk of dust and gas holds the blueprint for an entire planetary system. This is the 21st story in our celestial anthology, a protoplanetary disk caught in the act of creation, its intricate structure revealed by infrared telescopes peering through the cosmic haze. Unlike the polished orbs of mature solar systems, these disks are messy, dynamic places where gravity, turbulence, and magnetism sculpt raw material into worlds. The light we see today left this stellar nursery when Earth's continents were still forming, offering us a time capsule of our own solar system's chaotic beginnings. What makes these disks extraordinary isn't just their appearance like cosmic vinyl records with dark grooves and bright rings, but what those patterns signify. Those gaps aren't imperfections, they're construction zones. As microscopic dust grains collide and stick together, they snowball into pebbles, then boulders, eventually clearing paths like celestial bulldozers. Some gaps may already host infant planets, their gravity sweeping up debris like interstellar janitors. Others might be pressure waves, where the disk's own physics creates eddies and traps material like a cosmic conveyor belt. Each ring tells a story of growth, a snapshot of how randomness can give rise to order over millions of years. The real magic lies in the chemistry. These disks aren't just inert rock factories, they're bubbling cauldrons of organic molecules. Telescopes have detected water ice, carbon monoxide, and even complex hydrocarbons like methanol swirling in these nurseries. The same ingredients that, in our solar system, became the building blocks of oceans and life. Some disks show startlingly uneven distributions, with frost lines where water transitions from gas to ice, creating reservoirs that might one day fill alien worlds with lakes or oceans. It's as if the universe has recipe books scattered across the galaxy, each disk following slightly different steps to bake its own batch of planets. Then there's the diversity. No two protoplanetary disks look alike. Some, like H.L. Tauri's iconic rings, display razor-sharp gaps that suggest young planets already at work. Others, like the disk around the star TW Hydra, show spiral arms, possible signatures of hidden gas giants stirring the pot like celestial spoons. A few even exhibit misaligned rings, hinting at turbulent pasts where stellar flybys or sibling stars yanked the disk askew. This variety demolishes the old idea of planet formation as a neat, orderly process. Instead, it's a messy, competitive free-for-all where chance encounters and local conditions shape each system's fate. What's humbling is how much these distant disks mirror our origins. The same physical processes that carved gaps in H.L. Tauri's disk likely shaped our asteroid belt and the spacing between Earth and Mars. The organic molecules we detect there are the cousins of compounds that seeded life on our planet. When astronomers study these structures, they're not just observing alien nurseries, they're running a cosmic paternity test, tracing the lineage of our own solar system back to its dusty cradle. Yet the most tantalizing thought is this: right now, in some disk around a young star, another Earth might be taking shape. The same forces that assembled our world from chaos, gravity, chemistry, time are at work there too. Whether any of these nascent worlds will develop life or even survive their violent youth remains unknown. But the mere possibility transforms these disks from scientific curiosities into something profound. They're the universe's workshop, where raw stardust gets forged into futures we can only imagine. And the light arriving now, after its billion-year journey, is our invitation to watch the process unfold in real time. Galaxies aren't the solitary islands we once imagined. They're ravenous cosmic predators, locked in a slow-motion dance of consumption and rebirth. Right now, in a corner of the universe billions of light-years away, a massive spiral galaxy is tearing apart a smaller companion, their gravitational embrace stretching starlight into surreal arcs and streams. This isn't destruction, it's transformation. The smaller galaxy stars aren't being annihilated, they're being absorbed, repurposed into the larger galaxy structure like bricks salvaged from an old building. The light reaching us today captures this celestial feast mid-bite, a snapshot of a process that will take hundreds of millions of years to complete. What makes these mergers extraordinary isn't just their violence, but their inevitability. In the early universe, galaxies were packed closer together, like commuters on a crowded subway. Collisions were frequent, even necessary. Each merger injected fresh gas, triggering bursts of star formation and reshaping galaxies like cosmic pottery. The majestic spirals we admire today, including our Milky Way, likely grew by cannibalizing smaller neighbors, their delicate arms sculpted by these ancient encounters. Even now, our galaxy is digesting the remnants of the Sagittarius dwarf spheroidal, a tiny companion stretched into a stellar stream, wrapping around us like a celestial serpent. The mechanics of galactic digestion are both brutal and beautiful. As the smaller galaxy approaches, tidal forces stretch it into ribbons of stars and gas, a process called spaghettification. Some material splashes into the larger galaxy's disk, creating ripples that propagate outward like waves in a pond. Other stars are flung into elongated orbits, forming vast shells or diffuse halos that linger for billions of years. The most telling signature, distorted light. Gravitational lensing bends the victim galaxy's starlight into arcs and rings, while shock waves from colliding gas clouds glow in X-rays, painting the scene in invisible ink. Yet mergers aren't just about growth, they're about renewal. The influx of fresh gas reignites dormant star-forming regions, birthing brilliant blue clusters that stand out against the older stellar population. Supermassive black holes at the galaxy's centers, once quiet, awaken to devour the sudden bounty, powering quasars that outshine their host galaxies. These outbursts can blow away remaining gas, eventually quenching star formation and leaving behind a red, dead elliptical galaxy, a fate that may await our Milky Way when it collides with Andromeda in 4 billion years. The most fascinating twist, these events are cosmic recycling at its grandest. Stars from the devoured galaxy don't vanish, they mingle with their captors, carrying the chemical fingerprints of their birthplace. Some may even harbor planets now adrift in a new galactic neighborhood. Imagine a world orbiting one of these stolen stars. Its night sky would slowly transform, the constellations of its birth galaxy fading as new patterns emerge, a celestial culture shock playing out over generations. What's humbling is how these mergers redefine time. The light we see today from colliding galaxies left when Earth's continents were still molten, before life had even begun its experiments with single-celled organisms. By now, those galaxies have likely completed their dance, merging into something unrecognizable from their original forms. We're not just watching a snapshot, we're witnessing a frame from a movie that's been playing for eons, one where the universe constantly remakes itself through violence and beauty. So the next time you gaze at a majestic spiral galaxy, remember, Its graceful arms might be the scars of ancient battles, its brilliance the spoils of cosmic conquest. The universe doesn't waste its cataclysms, it uses them to build, to create, to weave new stories from the threads of the old. And somewhere out there, another merger is underway, its light already racing toward us, carrying news of a feast we'll only witness in the distant future. These 22 stories written in Starlight aren't just scientific curiosities, they're pages torn from the universe's autobiography, each one carrying revelations that took billions of years to reach us. Think about that for a moment. When you stand under the night sky, you're not just observing distant objects, you're engaging in cosmic time travel, catching whispers from epochs when Earth was unrecognizable, when the very atoms in your body were still fused inside long-dead stars. The photons striking your retina tonight might have begun their journey before dinosaurs walked the planet, or during the birth of our galaxy's spiral arms. What makes this cosmic library so extraordinary is how it reshapes our sense of connection. That quasar's light, it passed through interstellar gas clouds that no longer exist. The glow from a colliding galaxy, it reveals celestial structures that have since merged beyond recognition. Even the faintest red dwarf's flicker carries chemical signatures from a time when our solar system was just a swirl of dust. Every point of light is both a relic and a revelation, proving that the universe doesn't hide its history, it beams it across the void, patiently waiting for civilizations to develop the tools to decode it. And the most thrilling part, we've only just begun reading. New telescopes like the James Webb Space Telescope are essentially time machines, peering further back than ever before, to an era when the first stars were still flickering to life. Future observatories might detect the faint afterglow of planets that formed in the universe's infancy, or catch chemical traces of atmospheres that haven't existed for eons. Every technological leap doesn't just advance our understanding, it adds new shelves to this galactic archive, revealing chapters we didn't know were missing. But here's the profound truth hidden in these celestial narratives. You're part of the story too. The carbon in your DNA, the iron in your blood, the calcium in your bones, all were forged in stellar furnaces and scattered across space by explosions like the ones we've explored. When you gaze at the Orion Nebula or trace the arc of the Milky Way, you're not just an observer. You're the universe's way of looking back at itself, a collection of ancient stardust that has, against impossible odds, become conscious enough to ponder its own origins. So the next time you step outside on a clear night, try this. Pick one bright point of light, any star, any galaxy, and remember that its light is an invitation. An invitation to wonder, to explore, to connect across time and space. These 22 stories are just the beginning. Countless more are still streaming toward us, their light racing through the void at 299 million meters per second, each one a promise that the cosmos still has secrets to share. Now it's your turn. What cosmic story resonates most with you? Is it the rogue planet wandering endlessly between galaxies, or the pulsar's precise heartbeat echoing across the ages? Drop your favorite in the comments, and if you've enjoyed this journey through time written in Starlight, hit that subscribe button to join us for more adventures where science meets wonder. Until next time, keep looking up. The universe has been writing its epic for 13.8 billion years, and you've got the best seat in the house to watch the next chapter.